And I believe that we need an international organization that will make policy decisions about such an object. We are worried about existential threats from artificial
April
intelligence.
2026. NASA's most advanced robots vanish from Mars just as Harvard scientists issue urgent new warnings, and astronomers admit 3Pi/Atlas, an interstellar object, is breaking every rule in the book. Signals drop out, data warps. Official explanations don't add up. But what if a single cosmic visitor now links NASA's lost communications, Harvard's suspicions, and a comet that behaves like nothing we've seen before? The stakes, our ability to watch Mars, our understanding of interstellar travelers, and maybe much more. If Atlas is hiding a mission, what aren't we supposed to see? And how much danger are we really in? April 14th, 2026. Inside the Jet Propulsion Laboratory, a routine shift unravels. Perseverance, the flagship rover on Mars, misses its scheduled check-in. Curiosity, nearly a decade into its mission, drops from the Deep Space Network's Madrid complex without warning. Engineers scan console logs, packet loss spikes, handshake failures, and a string of no-data flags ripple through the system. At 0334 Universal Time, all communications with surface assets vanish. Telemetry from the Mars Reconnaissance Orbiter and the Trace Gas Orbiter, usually the backbone of Relay, begins to show corrupted timestamps and spectrum distortion. Automated scripts attempt to re-establish contact, cycling through backup frequencies and redundant hardware paths. Each attempt returns the same result: silence. The Deep Space Network, a triad of antennas stretching from California to Spain to Canberra, is designed to catch even the faintest whisper from Mars. Its sensitivity is legendary, capable of detecting a billionth of a watt. Yet, for 36 hours, the network records nothing but static and error codes. JPL technicians cross-reference solar weather bulletins. No major flares, no coronal mass ejection. The usual culprits: solar conjunction, scheduled maintenance don't fit. Shift leads annotate the outage as unexplained anomaly, noting the absence of any solar or terrestrial interference. Inside the Madrid control room, engineers replay the sequence. The loss of sync occurs simultaneously across multiple antennas, a pattern not seen in previous blackouts. Data packets sent to Perseverance and Curiosity never receive confirmation. Automated health checks, programmed to ping at regular intervals, fail to trigger any response. The Mars Trace Gas Orbiter, orbiting high above, logs spectrum distortions in its downlink, a kind of digital haze that resists decryption. The system's fragility becomes clear. Every command, every byte of data, depends on a cascade of successful handshakes: Earth to orbiter, orbiter to rover, rover back to orbiter, then to Earth. A single break in the chain, and the entire network falls dark. For mission controllers, the blackout is more than a technical glitch. It's a reminder that Mars, despite decades of robotic presence, remains a world just out of reach. When the signals vanish, so does our window into its secrets. Official statements arrive in clipped, practiced language. NASA's press office attributes the blackout to solar interference, a phrase that appears in every public update, despite internal logs showing no solar activity of consequence. The term surfaces again in a press release at 9 a.m. UTC, paired with reassurances about system redundancy and the promise of a full review. The explanation feels routine, almost rehearsed. But inside the engineering chat threads, the mood is anything but settled. A string of redacted emails, later released under the Freedom of Information Act, reveals a different tone. One systems analyst writes, "Solar angle doesn't fit. DSN-SNR's flat. This isn't a conjunction." Another, flagged by a shift supervisor, notes, "All communications dropped at once, across bands, across assets. Never seen that outside of a hard DSN failure, and DSN logs say hardware nominal." Rumors circulate in the JPL break room. Some engineers quietly speculate about a software bug, a configuration error, or a hidden cyber attack. Others point to the timing, how the blackout window aligns with a spike in photometric activity from 3I/Atlas, logged by amateur astronomers and professional observatories alike. Still, the official line holds. Press briefings stick to engineering review ongoing. The discrepancy between public messaging and internal chatter grows more apparent as the hours pass. A mission planner, off the record, refers to the event as the cleanest dirty anomaly we've ever had. The phrase spreads among staff, a shorthand for a failure that fits no known template. NASA's leadership resists speculation. In a town hall streamed to agency employees, the administrator repeats, "We have no evidence of external interference. Our teams are reviewing all possibilities." Yet, the incident logs, annotated in the margins by night shift techs, tell a more complicated story, one where the usual suspects are ruled out and the remaining explanations grow thin. As the blackout drags into a second day, the search for a cause turns outward. Eyes shift from console diagnostics to the sky, to the coincidence of a distant object growing brighter just as Mars falls silent. The official narrative holds, but among the engineers, doubt settles in, persistent as static. August 21st, 2025. The Minor Planet Center posts a new discovery alert. A faint, fast-moving object captured by the Atlas survey in Hawaii. Designated 3I/Atlas, its trajectory is unmistakably interstellar. Velocity and eccentricity place it beyond the sun's grasp, bound for a single pass through the solar system. Astronomers tune their instruments expecting a cold, inert rock. Instead, the first stacked images reveal something unexpected, a diffuse green coma, already glowing at 6.4 astronomical units from the Sun. That's farther than Jupiter, a region where solar heat is too weak for typical cometary activity. Time series photometry from Pan-STARRS and amateur observers across Europe confirm the anomaly. Over a span of nights, the coma brightens and expands, defying expectations for an object this distant. Spectral analysis from the Nordic Optical Telescope and Gran Telescopio Canarias picks up faint C2 emission, the molecular signature responsible for the eerie green hue. Normally, C2 appears only when comets approach the inner solar system, as sunlight cracks apart more complex ices. Here, it's present before the object has even crossed the orbit of Saturn. Chemistry offers only partial answers. Carbon dioxide and other supervolatiles can drive activity in the cold, but the measured flux is low. The coma's intensity and the rate of dust ejection outpace the gas detected. A deeper puzzle emerges when the emission lines are compared. Nickel appears without iron, a ratio not seen in other comets, interstellar or solar system. The data suggest a composition shaped by a different stellar nursery, or perhaps by processes no one has modelled. The object's brightness to mass ratio stands out. For its estimated size, no more than half a kilometre across, 3I/Atlas is shedding dust at a rate that rivals much larger bodies. Calculations using photometric proxies like AFRHO yield values near the upper end for any known comet, while the inferred bulk density is so low that some researchers propose a structure riddled with voids or macrocavities. The idea of a highly porous, even hollow nucleus gains traction. At the Minor Planet Center, each new observation is logged and cross-checked. The early activity, the green coma, the odd chemistry, all are flagged for further review. For now, the anomaly is undeniable. 3I/Atlas is active at a distance where comets should sleep, glowing with a chemistry that doesn't fit the script. The first clue that this visitor is not just another ball of ice and dust, but something fundamentally stranger, is already written in its light. The initial brightness curve for 3I/Atlas quickly defies prediction. Pan-STARRS logs the first light curve, expecting a gradual, solar-driven rise. Instead, the object's magnitude jumps erratically, surging by half a magnitude in a single night, then fading just as quickly. Zwicky Transient Facility, or ZTF, analysts, accustomed to the slow, predictable brightening of distant comets, flag the data for review. The pattern persists, a series of unpredictable spikes, some lasting hours, others stretched over days. Each flare is mirrored across observatories. No sign of instrumental error, no local weather artifact. Survey analysts at Pan-STARRS and ZTF begin cross-referencing their time-stamped stacks. On August 31st, 2025, a spike in brightness coincides with a stable, unperturbed trajectory. The object isn't tumbling or fragmenting. Its motion remains hyperbolic, velocity steady at over 57 kilometers per second. Unlike Oumuamua, which tumbled chaotically and showed non-gravitational acceleration, Atlas holds its course with minimal deviation. Attempts to model the volatility using standard comet outgassing equations fall short. The amplitude and frequency of the surges exceed what carbon dioxide or carbon monoxide-driven jets can explain at this distance from the Sun. The light curve's volatility, plotted against heliocentric distance, forms a scatter of peaks, each one sharper than the last. By mid-September, the object has already outpaced the total activity seen in Borisov during its entire passage, yet without the expected mass loss or visible signs of fragmentation. The Minor Planet Center's daily logs capture the growing confusion. Notes from the ZTF team reference unmodeled photometric excursions and non-periodic outbursts. Amateur astronomers, feeding their own data into global repositories, confirm the same unpredictable behavior. The consensus: Atlas is not just active, it's unstable, flaring and dimming with no regard for solar heating or orbital phase. By late September, the volatility draws attention from theorists. Some propose venting from deep cavities or a nucleus riddled with macropores. Others suggest a hollow shell, capable of storing energy and releasing it in bursts. The object's brightness-to-mass ratio, already flagged as anomalous, now stands as a central puzzle. For every surge, there's no corresponding shift in trajectory, no measurable acceleration. The object's path remains as stable as its light is erratic. The datasets stack up: Pan-STARRS, ZTF, amateur networks, all pointing to a rule breaker. Atlas refuses to behave like any comet, interstellar or otherwise. Its unpredictable luminosity is not just a curiosity, but a signal that something fundamental, perhaps structural, sets this object apart. Peer review rarely sparks headlines, but the Harvard-Smithsonian team's preprint on 3.1/Atlas draws immediate scrutiny. Their calculations begin with a puzzle. For an object estimated at just half a kilometre across, the measured brightness is off the charts. Standard comet models use proxies like AFRSO to relate dust production and nucleus size. Here, the numbers refuse to line up. Photometric curves suggest an active surface area far greater than the mass would allow, unless the bulk density is astonishingly low, between 0.1 and 0.4 grams per cubic centimetre. That's lighter than aerogel, and well below the fluffiest solar system comets ever measured. The team's lead author, Dr. S. Hibbard, presents a model built on voids. Their structure: a nucleus riddled with macrocavities, vast hollow spaces making up more than 60% of its volume. Spectroscopic imaging from the Gran Telescopio Canarias, a Nordic optical telescope, shows a stable rotation, with no evidence of the chaotic tumbling seen in Oumuamua. If the nucleus were just a weakly bound rubble pile, it should fly apart under its own spin. Instead, 3I/Atlas holds together, even as dust and gas surge from its surface. Anonymous reviewers, including planetary scientists from the University of Arizona and the Max Planck Institute, push back. They argue that mass estimates are indirect, and that outgassing from deep fractures or super volatile pockets could explain the activity spike. Hibbard's team counters with rotational stability curves and the persistent brightness-to-mass ratio, which remains 3 to 5 times higher than any known comet. The preprint's most controversial line is buried in the discussion. A hollow interstellar object, if confirmed, raises the possibility of non-natural origin. No one claims evidence of design, but the debate over cavities, porosity, and stability reopens old questions about what interstellar objects can be. For the Harvard group, the math refuses to quiet the possibility that 3I/Atlas is more than just a relic of distant star-forming clouds. October 2017. A dim, cigar-shaped object sweeps across the inner solar system at nearly 90,000 kilometers per hour. Astronomers at Pan-STARRS flag it as 1I/Oumuamua, the first interstellar visitor ever detected. Within days, the object's trajectory and speed confirm it cannot be from our solar system. Observatories scramble to collect data, but Oumuamua is already fading. No cometary tail, no outgassing jets. Yet, as it rounds the Sun, its path bends in a way that defies gravity alone. The acceleration is real, measurable, persistent, and unexplained by solar radiation pressure or known comet physics. Avi Loeb, chair of Harvard's astronomy department, steps into the fray. At a packed press conference, he lays out a hypothesis that draws sharp lines across the scientific community. Oumuamua could be artificial, a light sail perhaps propelled by sunlight or some lost technology. The idea is radical. Traditionalists counter with models of icy fragments, hydrogen icebergs, or dust pancakes. But none fit all the data. Loeb's argument is simple. The odds of seeing such an outlier so soon after beginning systematic sky surveys are astronomically low if these objects are natural debris. He points to the lack of a visible tail, the tumbling motion, the non-gravitational acceleration. Nature doesn't repeat such strangeness this quickly, he writes in a widely circulated email. We may be witnessing an interstellar message, not an accident. The debate spills from journals to headlines. Some call it a new era for SETI, others dismiss it as science fiction. Loeb stands apart, insisting that the scientific method demands open consideration of all possibilities, however unlikely. The controversy sets a precedent. From now on, every interstellar visitor will be scrutinized for signs of artificiality. When 3I/Atlas arrives less than a decade later, with its own suite of impossible traits, the echoes of Oumuamua's mystery are impossible to ignore. Two anomalies, separated by years, both challenging the boundaries of natural explanation. The pattern is no longer just an academic question. The search for intent in the data becomes a scientific imperative. March 3, 2026. Photometric logs from Pan-STARRS and the Zwicky Transient Facility capture a pattern that refuses to blend into the background noise. Every 16.8 hours, 3I/Atlas brightens and dims in a rhythm so precise, it draws immediate attention from both professional astronomers and a sprawling network of amateurs. The pulse isn't a single spike, it repeats, a train of luminous surges that persists for days, each cycle mapped out in overlapping light curves from telescopes in Hawaii, California, and across Europe. The amplitude, nearly half a magnitude, exceeds what typical cometary jets can deliver, especially at this distance from the Sun. The timing is uncanny. The first major pulse lands within minutes of a sudden drop in Mars mission telemetry, as logged by the Deep Space Network. Amateur observers feeding their time-stamped images into global data repositories notice the same synchronization. The object's brightest phase aligns with the window when Perseverance and Curiosity fall silent. Cross-checks eliminate instrumental errors and local interference. The pulses are real, and they are global. Natural explanations surface quickly. Some propose a rapidly spinning nucleus with active vents exposed in regular intervals. Others suggest outbursts from deep, volatile-rich pockets, though the regularity and strength of the signal stretch the limits of known comet physics. The debate spills into online forums and preprint archives. A subset of the amateur community, veterans of exoplanet transit hunts and asteroid occultation campaigns, begin to model the light curve, searching for harmonics, phase shifts, any signature that might betray intent. For many, the question lingers: what kind of object pulses with such discipline, and why do its emissions coincide with the loss of Martian signals? The evidence stacks up in graphs and raw FITS files, a 16.8-hour cycle, photometric peaks, and a blackout on Mars. The possibility of deliberate signaling, broadcast, jamming, or something stranger moves from fringe speculation to a topic of serious, if cautious, discussion among those watching the sky. The James Webb Space Telescope's near-infrared camera imaging sequence from October 13, 2025, adds a new layer of complexity to the 3I/Atlas puzzle. Analysts at the Space Telescope Science Institute process the raw exposures, searching for evidence of fragmentation or dust clumps. What stands out is not a single, obvious split, but a set of faint, persistent sources that track alongside the main nucleus for more than a week. At first, these appear as background noise, transient specks in the glare of the coma. But after stacking images from multiple orbits, the pattern becomes harder to dismiss. The same dim clumps maintain their relative spacing, moving in concert with Atlas as it races through the outer solar system. Relative motion modelling, led by Dr. Lian Shu's team, isolates these companions from both background stars and random debris. Orbital simulations show that natural comet fragments, once ejected, should drift apart rapidly, spread by solar tides, radiation pressure, and outgassing jets. Instead, these secondary sources hold their geometry, neither dispersing nor falling behind. Over 17 days, their separation remains nearly constant, with deviations well below what standard fragmentation physics predicts. Ground-based telescopes in Chile and Hawaii running in parallel confirm the persistence of these clumps. Pan-STARRS and Gemini North supply independent astrometric tracks, matching the James Webb Space Telescope detections within arcseconds. The Minor Planet Center's logbooks note that, unlike the chaotic debris seen after comet breakups, these bodies don't fade or scatter. Their light curves are steady, lacking the telltale flicker of tumbling fragments. Within the James Webb Space Telescope analyst group, theories multiply. Some propose a cluster of boulders ejected in a rare, low-velocity event. Others point to the possibility of internal cohesion, perhaps icy bridges or electrostatic forces at play. But the regularity of the formation and its endurance across weeks keeps the door open to more speculative ideas. The evidence mounts. Whatever these companions are, their behavior stretches the limits of natural explanation. Methane on Mars has always been a puzzle. On March 17, 2026, Curiosity's tunable laser spectrometer logs a reading that eclipses every prior spike, 21 parts per billion, nearly double the rover's previous record. The value stands out not just for its magnitude, but for its timing. The spike is registered less than 36 hours after the last confirmed signal from the Perseverance rover. Mission scientists at JPL flag the event for urgent review. MAVEN, orbiting high above, sweeps through the same sector and records a brief ultraviolet glow stretching across the northern hemisphere. The aurora, faint but unmistakable, appears in MAVEN's logs as a series of UV flashes, each lasting only minutes. Atmospheric models run in parallel by teams at Goddard and the University of Colorado fail to find a solar driver strong enough to account for the event. No coronal mass ejection, no spike in solar wind. Dust sensors on Curiosity's deck, meanwhile, pick up a surge in airborne particulates, levels usually seen only during the onset of a regional dust storm. Yet satellite imagery from the Mars Reconnaissance Orbiter shows no storm system in the area. The data points refuse to settle into a tidy explanation. Some researchers suggest a coincidence, seasonal methane release, an unmodelled auroral flicker, a rogue dust devil. Others, like Michio Kaku, voice a different possibility in a televised interview. Mars's atmosphere is so thin, so delicately balanced, that even a subtle nudge from interstellar dust or energy could set off a cascade. We may be seeing the first fingerprints of an object passing close by, before it ever arrives. Official mission reports stress caution. The methane spike is logged, the aurora catalogued, the dust event noted, but the cause remains unassigned. As the days pass, the Martian atmosphere settles back to its baseline, yet the sequence, methane, aurora, dust, remains in the logs, a trio of anomalies timed too closely to ignore. The question lingers: did Mars react to a cosmic visitor before the world even noticed? 3 objects, 3 sets of rules broken in succession. In 2017, astronomers watched as 1I/Oumuamua swept through the inner solar system. No tail, no coma, just a tumbling, cigar-shaped body accelerating in ways that gravity alone could not explain. 2 years later, 2I/Borisov arrived, hyperactive, shedding gas and dust at a rate that dwarfed most known comets, but ultimately behaving within the boundaries of natural physics. Then, in August 2025, 3I/Atlas is discovered. From the outset, it stands apart. Active at 6.4 astronomical units, glowing green in the cold, its brightness surging unpredictably. Its structure is so porous that density estimates drop below 0.4 grams per cubic centimeter, lighter than aerogel. The anomalies stack up: stable trajectory, rhythmic pulses, companions that refuse to disperse. Neil deGrasse Tyson, speaking in a televised panel, puts it plainly: each visitor is stranger than the last. Oumuamua bent our models, Borisov stretched them, Atlas shreds the manual. He gestures to a timeline chart, 2017, 2025. Each arrival closer, each set of anomalies more difficult to fold into comet theory. The escalation is not just in the physics, but in the pressure on institutions to respond. NASA's official lines grow more cautious, while Harvard's theorists grow more bold. The scientific community, once content to treat these as rare cosmic flukes, now faces a pattern that resists easy dismissal. Atlas, by every metric, sits at the top of the anomaly scale, a visitor that demands new answers and perhaps new questions. NASA's Public Affairs Office stands by its script. At each press conference, the phrase repeats: engineering glitch, solar interference, no evidence for external disruption. The explanation lands with practiced calm, even as internal engineering logs circulate with words like anomaly and unprecedented event. When pressed by reporters, the agency's spokesperson insists on technical causes: aging relay hardware, routine solar weather, the expected noise of deep space. The message is clear. There is nothing here that challenges the boundaries of standard mission risk. Harvard's press office, by contrast, takes a different tack. In interviews, Avi Loeb and his colleagues draw attention to the brightness-to-mass ratio, the hollow structure hypothesis, the rhythm of Atlas's pulses. Loeb, never one to hedge, points to the coincidence of lost signals and photometric surges. He calls for open data, for international review, for the possibility, however remote, that Atlas is not just an outlier of cometary physics, but a candidate for purposeful design. Academic papers circulate with language that is careful but provocative. Macrocavities, non-natural stability, design cannot be excluded. Behind the scenes, the divide grows sharper. NASA's internal guidance, leaked in fragments, cautions staff to avoid speculation and to refer only to peer-reviewed naturalistic explanations. Harvard's researchers, meanwhile, publish preprints that edge closer to the line between natural and artificial, inviting scrutiny and, at times, ridicule. The debate spills onto social media, into science podcasts, and across the desks of policymakers. Each side accuses the other of overreach. NASA of stifling debate, Harvard of courting headlines. The stakes are more than academic. If Atlas is natural, the mystery is one of physics. If it is not, the implications are planetary. Avi Loeb, in a televised panel, puts it bluntly: if you always assume nature, you risk missing the message. If you always assume design, you risk fooling yourself. But the data demand we ask both questions. The NASA administrator, when asked to respond, offers a single line: we follow the evidence, and the evidence supports a natural origin, so far. The tension is no longer just scientific. It is a contest over who gets to define the unknown. Stacked evidence now draws a line through every anomaly. Signals from Mars vanish in lockstep with Atlas's pulse, timing that resists coincidence. The object's brightness, measured against its mass, stays impossibly high, as if most of its bulk is empty space. Harvard's calculations refuse to settle for rubble or fractured ice. In Avi Loeb's words, written to colleagues in late 2025, nature doesn't repeat such strangeness so soon. We may be witnessing an interstellar message, not an accident. The formation of companions, tracked for days without drifting apart, deepens the puzzle. Standard cometary fragments scatter quickly, pulled by sunlight and outgassing jets. Here, the geometry holds. The companions move with the main body, their spacing too regular for random debris. Every dataset, photometric, astrometric, spectroscopic, feeds into a model that looks less like a comet and more like a system. A structure built with intent, hollowed out, accompanied by bodies that behave more like deployed assets than natural fragments. No single clue stands alone. Lost signals, hollow interior, organized companions, all align at the moment Mars falls silent. The pattern resists natural explanation, even as official voices urge caution. The question is no longer whether Atlas is an oddity, but whether it is acting with purpose. If so, the blackout may not be a side effect, but a warning. The dark secret at the heart of Atlas is not just what it is, but what it intends. On April 14, 2026, NASA's Mars missions experienced a 36-hour blackout, with error rates and lost signals documented across multiple assets. During the same period, telescopes recorded rhythmic energy pulses from 3I/Atlas, the third confirmed interstellar object, whose activity and structure defied known comet behavior. Harvard's published analysis pointed to a hollow interior, with brightness-to-mass ratios that could not be explained by standard models, and images from JWST revealed persistent companion bodies moving in formation. Yet, official statements from NASA describe the anomalies as engineering glitches or solar interference, leaving critical questions unresolved. Why do these interstellar visitors keep breaking the rules, and what caused the Mars blackout to coincide with Atlas's surge? To date, no peer-reviewed study has provided a unified explanation. As Atlas approaches Mars, the scientific record stands: signal disruptions, atmospheric changes, and a growing divide between institutional responses. The facts remain public, but the full meaning behind Atlas's dark secret is still unknown.